Hello everyone, I am welcoming you all once again to this channel. Today I am going to make a video on our VASP tutorial series where we will mainly see this how to do this DOS and band structure analysis, and also we will try to plot the density of state and the band structure using some softwares, and also we can also plot them using a code. Okay, so here I have these files over here. You can see that to calculate this band and DOS we need 4 such steps, and in the very first step we have to optimize the structure. So here I have taken the silicon structure over here, that is the bulk silicon structure, which is of cubic type. So before going ahead with the video, I am first going to show you that how you can find out this structure. So here in the materials project, you can simply go to this materials, this exploring materials, and here I am typing this silicon, and the very first structure we have found as this cubic one, and which is also verified from both experimentally and theoretically. So I am opening this. So here you can simply download this CIF symmetrized file. So this is the CIF file we have downloaded now, and this is the file I already have it here. And if I will go to this first and I will open this CIF file. So I am opening it in my Vista. So you see, this is the CIF file that we have downloaded, and this bulk silicon structure has this diamond crystal type structure, and but the lattice vector for this is cubic type. And here you can simply go and start export, and we can export this to Postcard simply. Okay, save it. Okay, so you see one Postcard VASP came, and this is how it looks like. And now I am also going to open this Postcard over here, and you can also see that some atoms are also appearing apart from this boundary. So we can change this by here. So apply. So you see that all the boundary atoms are not appearing right now. Okay, so this is how we can convert this simply the CIF file to Postcard first, and this Postcard we will take for further calculation. So I am renaming this postcard.vas to simply Postcard. Okay, so now with this as a Postcard, and here I have taken some in-car parameters simply for the optimization thing. So you can check it over here that yes, so you see that the structure that we have taken is silicon, and here we are going to do the silicon optimization, and the precision for that is accurate, and isometry we have chosen as 0. And you can also see all those comments over the VASP wiki. So I am not going in detail for this simple optimization, but still I am showing that what is this isometry doing here. So this isometry is only which determines the symmetry for the VASP calculation, and the value isometry is equal to 0 we have taken, because we don't here for isometry equal to 1, -1 or 0 it uses the symmetry switched off. Okay, so we are not considering any symmetry over here. And this is the EN cut, that is the energy cutoff value, but this is 320 here. So how I have taken that? So here I am going to open the Postcard file. So simple the PB Postcard file for the silicon one. So you see that this is the POW PB kind of Postcard file that we have taken, and here the EN max is 245 and EN mean is 184, and this 130% of this EN max we have taken, and that value is nearly this 320. Okay, next is this NELM. All of us we know that this is number of electronic step, and this I smear we have chosen a Gaussian smearing. This is a sigma value, and this is ISIF3. So where we are doing all the calculation, like all the relaxation over the atomic position and also along the volume. also we are allowing the volume change. And here this IBRAON equal to 2, that is this conjugate gradient approximation. And next is this NSW, number of ionic steps, and this is the force and energy cutoff and all those. So here we are not going to write any of our files, so only simple optimization thing we will perform over here. Okay, now also, so after that we have also chosen the K points here. So the K points we have chosen as this Moncrief pack, and the value we have taken, K value we have taken as 11 11 11, a kind of a compact grid over here, like for better relaxation. And now after having this in-car, post-car and in-car, and this is our post-car, and the K points here I have shown, and the same simple PV port-car, I have optimized this structure, and here is my output, and here I have found this cont-car and other like output files as well. So I am going to open this post-car and the cont-car at a time using VASP software, so that we can see what is the difference that occurred after the optimization. So here I am opening that. You see that this is our postcard. Let me first remove these bonds for both of these files. Okay, so you see that, so this was our postcard that we have given, and in the summary you can check that this is of cubic type, so all this alpha beta gamma is 90, and here the value was earlier for 5.44 and 44 angstrom, that is this lattice constant. And here after optimization you can see that the lattice constant value is now 5.466, and this is also same, and the value of this angles like alpha beta gamma is also 90, that means this is also cubic, and this structure is now relaxed and it has reached up to its correct lattice constant. Okay, so this way we can see that what is the difference between after optimization and before optimization, and this part is clear. Now let's go and let's go to our next step. So here I am going. So this is the first part of this calculation is done now, like we have done the optimization for the silicon. Now after this optimization reaction, whatever the file we have got as a cont-car, this file we will use as a post-car for our next calculation. So here I am simply renaming the cont-car to post-car, and I will use this cont-car as a post-car in all further steps. Okay, so here you can see that the second step is known as self-consistency calculation. So here what we want to do mainly, so in the in-car it will be very much clear that you see that here we just want to save the wave car and the charge car file for further analysis. Okay, so here we have to do nothing, rather we need to do a simple single ionic step calculation, so that we can have our wave car and charge car to be saved. And similar way we have set our parameters, like here you can see that instead of NSW 200 or something, we have set only to 0, and here also I have commented out this ISIF3 because we don't want any optimization, rather we just want a single SEF to be run. And here you can see that IBRAON value also we have taken as -1, and why it is that I will show you over here. So this IBRAON equal to -1 to avoid the to prevent the computing for the same structure. So we don't want to compute the same structure again and again. That's why this kind of parameter I have set. So if you will not set, that will also not impact that much. And now here L wave is equal to 2 and L charge is equal to true we have given, so that we can have our charge density and wave car file to be written. So this part is clear now. So after this I have also run the calculation, and here in the output file I have found this charge car and here is our wave car. Now this step is very simple. Just to save this charge car and wave car, we have done this step. Now to the further step, we need to use this charge car and wave car in our further step. So I am going to take these files. So one is this charge car and one is this wave car to the next step. So here in the third step, I am going to keep them over here. You can do, I am doing it from my like from here. You can also do the same using the terminal, and that is a better way to do. So here you can also see that what we have here, we have charge car, wave car and postcard. This is the same postcard that we have saved from the count car of the first step, and this postcard will remain in the second, third and fourth step as well. Okay, so and here some changes we have made in our in-car file that I am going to show you over here. And this third step is to find out the density of state. So here I am opening the in-car. So you see that all these parameters, these are the same as we have given earlier. Rather, we have given some extra parameters like this I start, I charge, this L orbit, any DOS, all this. So we will see all these one by one. So first thing is the I start one. So I am searching over here. So I start is one means it will read the wave car. So you see that I start is equal to 1. So restart the constant energy cutoff orbital. So this is mainly recommended to set when we have a wave car. So as you have seen that I have copied the wave car from the second step to here. So for that we have given this I start is equal to 1. And next is this I charge is equal to 11. So I charge 11 means what? So here you see that I charge 11 is to obtain the eigenvalues for the band structure or the density of state of a given density read from the charge card. So it will read mainly the densities from the charge card. So that's why this I charge 11 command we have given. And next all these commands are similar as it is. And next one is the L orbit. So what is this? So L orbit, you can see that this L orbit 11 we have given. That means it will write the DOSCAR and the PROCAR files. So these files we require to plot the density of states. That's why we have given this L orbit is equal to 11. And here another command over here we have given as any DOS. So what is this any DOS? So any DOS is nothing but the number of grid points of an electronic density of state and dielectric function. So here you see that the default value is 301. So the number of density of state points can be given as any DOS. So here we have given 1000, like there is no limit, just a number we have given. Okay, now next to that we have seen that these are the three commands that we have made as commented out. So what are them? So what are these? So here I am going to the second step now. Kindly see this carefully. So in the second step there is a file that has been generated as eigenvalue. So what is this eigenvalue and what it is telling us? So you see that in this file we can see that this number is representing our number of bands. So here you see that this is our number of bands that we have given as 32. And this particular column is representing, like this middle column is representing the energy values. So here the energy range is starting from minus 6.195 to 15, and in the next step also 15 point something. So this way it is going, and you can see up to the end of this file, and you can check that what is the minimum and maximum range within which the energy will vary. So based on that we have set our En min and En max as -8 and -16 respectively. So this way you can set one range. But here as we have commented out all these three tags, that means the entire calculation will be automatically choose this range, and it will automatically calculate this number of bands. So that's why I have just given it over here, so that I can tell you that what is this like what are these numbers. and how you can set your DOS and band structure range, energy range for them. So that's why I have given it over here, but you can skip them. Okay, and next this exactly similar thing we are doing, and here another thing is we don't want the L wave and L charge files to be written over here. Okay, and here you see, here also we have taken this NSW0 because we just want a single calculation to be performed, like single ionic step. Okay, now let's close all these and go to our third step. So here, after having all these things, I am going to show you the K points thing. So you see, earlier we have chosen the K point grid as 11 11 11, but now this grid is even denser and we have chosen it as 21 21 21. So this is because, this is mainly due to, like, we want to have a very finer density of state. Like, to have a very accurate calculation, you can increase this K grid. Okay, so that for that reason we have like increase this number over here. You see that this is 21 21 21. Earlier it was 11 11 11 only. Okay, so this is done. Now after performing this calculation with having charge car and wave car from the second step, and with some changes in the in car and K points, we found this as the output. So here, now what I will do, here it has written this procar and various other files, so which will help us to plot this density of state. Now first thing what I will do, I will first plot the density of state using the Sumo plot. So Sumo plot, all of you know that this is a very popular software to plot this kind of structures, and here I am using the simple command. So sumo hyphen DOS plot, and it will run for some time, and after that it will return us a figure where we can see our density of state. And let's give it some time so that it can generate in between. Yeah, so now the file has been generated, and here I found that dos.pdf is present over here, so I'm going to open it. So you see that this is the file that has been generated by the sumo plot, and this is how the density of state looks like. So the black color line is for the total DOS, and this purple, like this magenta one, is for this silicon s orbital, and this blue color one is for silicon p orbital. Okay, now this is a very automated plot. Now what I want to do is, here I have written one density of state code, so I am going to execute that code here. So here I am going to open this Python file. So here you see that, yes, so this is our code, and in the very first code what we have done, like we just want to plot the total density of state. So I am not going in detail with this code. You can see this is a very simple code from where we are using this VASP on XML as our input, and from there we are calculating our total density of state. So let's run this code. So it has some compilation time. Yeah, so it's done. Now this is the total density of state. Now I will we will do that comparison later. So now this is plot, like the total density of state has been plotted using this Python script, and here you can see that there is a shifting, like this is the Fermi energy level that we have shifted. Like here is the Fermi shift we have done, like the total energy minus the E Fermi energy, that level we have shifted. That's why here the label is coming. Next plot we can see, we can plot the total density of state as well as the partial density of state of each orbital. So here the code is compiling. Let's see what kind of figure it is returning. So here it is, you see that this is the total density of state, then the red one is for s orbital and the blue one is for the p orbital. Next here, similar kind of plot I have tried to generate as we got from the sumo plot. So here I am opening the sumo plot in one side, and here you see this is the returned plot from our Python code. And if I will open that simultaneously, you can check. Yes, you see that what is the difference in between these codes. So here the sumo plot gave a very automated code where the Fermi shifting was not, I think it has not taken into consideration, like Fermi shift is not taken into the consideration for the sumo plot, but here we have done the Fermi shifting. That's why our zero label and sumo plot zero label is different, but the entire plot is same. And also you can also say that why this is showing so many label, because the energy label for the sumo plot is only between -6 to +6, but here we have changed the energy label, and here the energy label is up to -15 or -12 to +10 or 12. Okay, so this way you can vary your x label and y label for the plotting. Okay, now this part is over. So the third step we have done with. Now the fourth one. So the fourth step is mainly for the band structure calculation. So here similar things we have done. So what to do? Again we have to copy this wave car and charge car file over here. So charge car and wave car I am copy. Let's keep them in the fourth structure, and this is same postcard. Here we need to see the incar. So here you see that the incar file we have taken is exactly same. Rather the only thing we have given as NELM1, because we just want a single single electronic step in a single ionic step, for which we have given NSW0, and for NELM1 means only a single electronic step will be the VASP will calculate the single step of electronic and ionic, so that we can have our band structure. And here nothing else we have given. Yes, this L orbit also I have shown earlier, that why we have taken this. This will write this pro car and Oscar and all, and yeah, that's it. Now now when I will like I have already done this calculation, and also another thing is this K point. So where is that? Here you can see that we don't have a K point here. Rather we need to generate that, because we don't know which kind of K path this structure will follow. So for which the main part in the band structure thing is here. So I am going to this fourth step, and here we need to give a path along which our K point, like our band structure, will be plotted. So for that we need to have a specific path, like gamma, M and various other paths are available. You must have been know, like these are nothing but the Brillouin zones of this for a particular structure. So we can't have a prediction for that or something. So so here I am not going to do, rather I am going to use the VASP kit. So I am going to my VASP kit. So here I have opened my VASP kit, and you see that there is an option K path for the band structure. So we are going to do this. We want our K path. So I am clicking on this 3 number. You see that here it suggests that 1D structure, 2D or bulk. So we have taken the cubic silicon, that is the bulk structure. So for which I am going to type as 303. This option is valid for us. And after that it has generated some files. You see that one is this high symmetry K points, which is like this, and next is this kpath.in, which is like this, and another one is primitive cell .vasp, which is like this. Why like what is the primitive cell? So the primitive cell of a silicon which has only 2 coordinates, that's why it has given for the primitive cell. and symmetry is also another file it has given. So now after seeing all these, which one is more relevant to us? That is this kpath.in. So although similar, this high symmetry points and this file is exactly similar, rather it has arranged in the form of a k point. So now what we will do, simply we will rename this kpath.in into k points. So I am renaming this. Okay, so this is the k points, and now here let's see what is this. So here the we want 20 number of I think lines or something in between some path, and here the reciprocal lattice that we are writing, first it is gamma x, then x and u, then k to gamma, then gamma to l, then l to w and w to x. So this is the path for the band structure that has been generated by using this VASP kit. And now after performing the calculation using this input file, so these are not our input is only charge car, in car, k points, port car and post car, and this web car, as we have given our input as I start 1 and L charge equal to 11. So now this is the output that we have generated after performing this calculation. And here say again the same thing I am going to do, using the sumo plot, we will try to plot the density band structure. So sumo hyphen band plot, band plot or band plots, band plot. So sumo band plot, I am clicking on the enter. So you see that we have got one PDF. So this is how the band plot has been done by this sumo plot. And next I have this code. I am going to run this code so that we can plot our band plots. So let's open that. And yes, there is also another option I forgot to mention over here. So here, if you don't have this seek path or something, this kind of command, you can install it from your Python, like pip install pymatgen matplotlib seek path. So everything will be done on this pymatgen module. Okay, so let's go. And here I am going to run this code again. So you see, this is the plot that has been given by our this Python code, and here also similar kind of thing. We can see that gamma, xu, whatever we have found from our sumo plot, exactly same. And this is the path that we have given. This you see that gamma, then x to u, then u to k to gamma. So this way, it has followed, whatever the way we have given this reciprocal lattice vectors, this way it has followed. I hope all of you have understood. And yeah, I have got so many requests to plot this DOS and band earlier and now also, and some of you have also requested to do the same kind of analysis using this HSC functional. So I will try to do that also. So okay, yeah, so thank you all and bye bye.